Right, this time for transition metals, we're going to be looking at ligands. We're going to be looking at what ligands are. We're going to be looking at how they attach themselves to transition metals, and we're going to be looking at how they are classed. We're also going to be looking at naming compounds that contain ligands. Okay, so this is a simple ligand. And what we're doing, first of all, is looking at our transition metal, which is what M is, and L is to indicate the actual ligands. If you look, they've all got a lone pair of electrons on them. These lone pair of electrons are being donated to the transition metal to form a dative covalent bond. Okay, so those 4 ligands would attach with 4 dative covalent bonds made from the lone pair of electrons, or the non-bonding electrons, on the L. We did cover dative covalent bonds earlier in this unit, but we're coming back to them at this precise second. So, our dative covalent bond, it's 2 atoms that are sharing a pair of electrons that come from one atom, and it's usually a lone pair on the atom that's donating them. Okay. We also have to remember, though, that our ligands may be negative ions. Okay, so they don't just form from molecules with a lone pair or atoms with a lone pair. It could also be a negative ion. If we look here, we've got an example of a dative covalent bond forming, just to remind us. We've got our ammonium ion. So if we had ammonia, we would have on it our hydrogen with 1 electron from the hydrogen and 1 from the nitrogen, another hydrogen, same, 1 electron from the hydrogen, 1 from the nitrogen, and the third one, 1 from hydrogen and 1 from nitrogen. Our final bonded hydrogen atom, those 2 electrons come from nitrogen, that's why they're circles, and it's a dative covalent bond. Around it, we've got our square brackets. Okay, the reason our square brackets are there are to indicate we've got a positive charge on that whole ion. So our ligands, they can be described or classed as dentate. Okay, tooth-like. Think it's as if they're biting into the transition metal. They used to use the term chelating, as in a claw rather than teeth biting, but we're concentrating on dentate, especially as when you name them, you need to put the term dentate into the actual word you're using. Okay. Now we've got different classes of them, and it depends on how many times the ligand bites into the actual metal. So we've got monodentate, so it would bite into it once, or it would attach with one cell, one cell, or one lone pair of electrons. Bidentate, bite in twice, so you've got 2 lone pairs attaching themselves to the metal. Now, it is possible for us to work out what the classification is of the ligand from either the formula or the structure of the ligand, or even the whole complex. Okay. Now, we've got to be careful. One of the things I did notice when we were looking at the past papers was that we forgot to check how many ligands were actually attached to the metal. Okay, we're quite a few slides in before that will actually come up. We'll go through the explanation far more before we get there. So this is an example of a bidentate ligand, because, or both of them are. If we look here, we've got our nitrogen with its lone pair, which are going to form one dative covalent bond there, and then we've got our second nitrogen with a lone pair forming the second dative covalent bond. Over on the oxalate ion, we have got our oxygens with a negative charge. If you look, technically, if it was a diacid, you'd expect, as it is, you're saying diacid because we've got 2 carboxylic groups, one that side, without. But if we look, this oxygen has already lost its hydrogen, giving the negative charge on the oxygen, and also why I was referring to it as part of a carboxylic group. Okay, again, this has got 2 places where it's going to bite in, or it's got 2 dentates to the transition metal. Happy with that? EDTA. EDTA is a chemical that you're going to come across quite a bit in advanced hard chemistry. It's actually used in titrations. It's used in analysis and trying to find out how much metal is in water or something like that in the substance. Okay, so if we look at this, now if we think back to the last example as well, when we actually join it on, these hydrogens are going to go, which is part of the reason why it's this oxygen. that is attaching itself to the transition metal. Because we could look at it and go, hang on, this one's going to be C double bond O. It's also got lone pairs. But no, we're doing this, and this hydrogen is going to be lost, and we're going to end up with a negative charge on each of these, and that's why it's that oxygen that's being used. Our nitrogen lone pair, so it can also attach there. Now, our EDTA, it usually attaches, or as far as we're concerned, it's going to attach in a 1-to-1 ratio with the metal, okay? So that means all 6 of these are going to attach themselves to the transition metal when it actually binds to it. This is what it would look like without the hydrogens. Just notice the negatives that should be there are missing, so that's not very helpful. But we've got our lone pair that's going to form, or a pair of electrons that are going to form the dative covalent bond showing. If we look here, this the C's, CH2s and the C's are missing. But this little line here will say represents this one here. So the line is showing that CH2, C with a double bond O, and then the final oxygen that's actually binding to nickel is this one there. Okay, top one we'll take to be the top line, and inside it would be your CH2, C double bond O. This line here would have the CH2 and the CH2 in it. This one here, go for the inside one, be this one, so CH2, C double bond O, and the oxygen binding to the nickel. And finally, this bottom one here will just say, for the sake of this diagram, is here. So it's CH2, C double bond O, and the other oxygen binding to the nickel. Okay, so each of those will be dative covalent bonds, and both the electrons are coming from either the oxygen, as is in the 4, and then the nitrogen for those 2. This is hexadentate because we've got 6 dative covalent bonds forming between the EDTA and the nickel. Next bit, we're looking at coordination number. We've got to be very careful with this, okay? Our coordination number is the total number of bonds from the ligand to the central transition metal. Please be careful because there could be more than one ligand being attached to that transition metal, okay? If we look back at the 1,2-diaminoethane on slide 7, so that's this one on the left-hand side, we can see that the coordination number here would be 2 because we've got 2 bonds forming here. Okay, so that one ligand is bidentate because it's got 2 places where it's joining itself or biting into the metal. And the metal itself has got coordination number of 2 because there are 2 bonds attaching to the nitrogen. If we look at EDTA, we can see that the coordination number 6, 1, 2, 3, 4, 5, 6, because those black lines are trying to demonstrate 6 dative covalent bonds. The reason that we have got the square going through the ones in the middle, or around the ones in the middle, is to try and help with the 3D shape, okay? That would be octahedral, wouldn't it? We've got the one at the top, the one at the bottom, and then the 4 in the middle. So that would be an octahedral shape. So it's then saying, slide 10 tells us that. Let's just hope that's the next slide. There, but this is what I want anyway. If we look here, this is slightly different, okay? Now, if we look at each of these cyanide ligands, we've got 6 of them. But each of these cyanide ligands is going to be monodentate because there's only one lone pair of electrons from each one biting into the iron, okay? However, the coordination number is going to be 6 because we've got 6 of them. Please be careful with that. It's not that we've got 6 of them, so it's going to be hexadentate. It's not, because each one is only biting in one, so it's monodentate. Our coordination number and the classification, the dentate of the ligand are not the same. If we look at this one, I've just seen I'm giving you the answers to the questions here. If we look at this one, nickel, it looks for I've not given you the oxidation number, sorry, I've only given you the coordination number. We've got 4 lines going in, which means the coordination number for nickel will be 4. And each of these ligands is not going to be tetra, dentate, it's going to be monodentate because each ligand is biting in once, and we're looking at each ligand separately in terms of classification of the ligand. When we're writing the formula or the name for the ligand, we need to think about how we're doing it. Okay? So what we need to do first is make sure we've got our complex ion written within square brackets. Okay? Within these brackets, we need to have our metal symbol written first. Then any negative ligands next to that. For that, I mean, if we had chloride, it's a negative ligand, it would go next. Then we've got our neutral ligands listed last. Okay. Now, if there's a charge on the overall ligand, it goes outside of the square brackets. For example, what we've got here is iron. That's our transition metal going first within the square brackets. Then we have got our two hydroxide ions. They've got the negative charge, so they go next. Remember, because there's two of them, we need a 2 there. Then we've got our water molecules. They're neutral, so they're being listed last. Okay, 4 of them. It then says that we have got a positive charge overall on this whole ion. This is important, this positive charge, because if we were not if, because it does ask you to do it, for working out the oxidation state, we know that Fe plus 2 times -1 for the OH plus 4 times 0 for the water gives us plus. Okay, so we've got Fe plus 2 minus plus 0 equals 1 positive. That would mean if I put my iron on its own, the oxidation state or the oxidation number is going to be 3 positive. Okay. In terms of our coordination number, I've got 2 plus 4, so I've got 6 ligands. So my oxidation number, sorry, not my oxidation number, my coordination number would be 6. Okay. I can't see it because we don't have a picture in front of us, but that's got a 1 negative, and we're only going to take one of the lone pairs off water. So each of these would be monodentate. Happy with that? Now, at the very bottom of the page, it's saying complexes like permanganate, MnO4, often have no brackets. We've only got one substance attached to manganese. That's one reason for it. Also, there's a possibility this itself is going to be used as a ligand attached to another metal. Okay? Right, in terms of naming the complexes, when we name them, we put the ligands first, but they have to be listed alphabetically. Okay? And then we list the metal last. So, there are other things we need to remember. Sorry, I should have included this first. I was going to start trying to name one. So, if we've got chloride, it's going to be listed first if the other one is something like nitrite. Sorry, I'm just going for both 2 examples that are on the page. Okay, if we had water in, though, watch water, the names change slightly. So water would have to go first, but if you look there, it's called aqua. So it would be aqua, chloro, nitroto. Okay, I need to go back to explaining these. If we look, it tells us if our negative ion ends IDE, we change IDE to O, which is where chloro comes from. If it ends ITE, we need to change the last letter, the last E to O. So nitrite, nitroto. I think I said that slightly wrongly. Nitrito, sorry. So there are other things we've got to watch for. If water is a ligand, we use aqua. If ammonia is a ligand, we use amine. Please be careful. When we did amines in higher in terms of our amine structures for proteins and the like, we only had 1 M. If we put 1 M in this time, it will be marked wrong by the exam board. Okay, when we're talking about ammonia, and it's a way to help us differentiate, when we're talking about ammonia as a ligand, amine must have double M. That's why it's underlined and in bold. If we're talking about carbon monoxide, we use carbonyl as the name. This is a summary of the ones that you really need to know. Right, now if there's more than one of the ligand, we'd use the right prefix. So if we go back to this screen, we've got 4 chlorines. So they'd be chloral in terms of the name, but also we put tetra in front of it because we have 4 of them. Next thing we need to think about is if we've got a positively charged complex, there's no special name ending. You would just use the metal that you've got. That's what that means, okay? So if it was platinum that had a positive outside, we'd say platinum. But we have to watch because if the overall complex, so outside square brackets, if we've got a negative, we need to change the name of the metal to end ATE. But we've got to also be careful because we use some Latin names. So if we have a negatively charged compound that's got iron in it, we don't say ironate, we use ferrate. I was going to have to go to the next page. I was going to say if it is negatively charged and it's going to be platinum, it'd be platinate. I was hoping platinate was there, but it's not. But there's the example. Okay, common ones which keep the first half are manganese changing into manganate, but you've met that in we've talked about manganate ions having a 2 positive charge, both throughout this and at higher. Okay, potassium permanganate being one good example that you've met before, MnO4. So should have said MnO4 minus, and that would have tied it in even better with this. Right, we need to look at our oxidation state. Remember, oxidation state and coordination number are not the same thing. We need to get our oxidation state, and we put that in Roman numerals after the name. Okay, it's still within brackets, and technically it's after the metal. And it's the metal that the oxidation state refers to. On the next slide, we've got an example, and then throughout the rest of this, we have got questions that you were to try. But remember rightly, I did work through some of them to try and help you out, and I colour-coded it to try and help. Right, we'll have a look at this one though and discuss it. So we've got our ammonia there. Amine, double M, keep it. There's 6 of them. That's why we've got hexa. There is only one ligand, but in terms of listing, you ignore the prefix, it is the ligand name. So no matter what I had there, the amine would have come first if it had other ligands, okay, even though I've got hexa. If I had aqua, if my alphabet is right, it would still be amine aqua. If it had 2 aqua, it would be di, okay, but it would still be hexa amine di aqua. Or if I was keeping it that nickel still had a coordination number of 6, I really should have said tetraamine diaqua. But the alphabetical order refers to ligands. We ignore the prefix. Then nickel, positive, so it keeps its own name. And to get the Roman numerals, we know it's got an overall 2 positive charge, so we need to deal with this. Our ammonia is a neutral ligand, so 6 times 0 gives us 0. Therefore, our nickel has the 2 positive. Okay. This one here, cyanate. Watch is changed to cyano. 6 again, hence hexa. Ferrate, it's a negative ion, so we need to change the end of iron to 8. But we also have to remember that fer is used, the Latin name's used rather than iron. They're -1, so 6 times -1 gives me -6. Iron plus 6 minus gives me 3 minus. Take my 6 minus to the other side, gives me 3 positive. Therefore, the oxidation number, their oxidation state is 3. As I say, the rest of these are the examples that you worked through. These ones are colour-coded to try and help you. And I've written down how to work out the oxidation number for these ones. Okay. These ones have just got the answers. If you're unhappy with any of them, please come back to me and ask for a better or a more detailed answer as to why it came up. Okay. This to me looks like the answers, at least to question 1A from page 40, and there's the rest of the answers. Question 2A has been worked through and shown why you've come out with the different bits. Okay. These ones, again, they weren't in your book, but it would be extremely helpful to make sure you have done them. There's my platinate from a platinum from earlier. Okay. There we go. There's the answers to them. Any questions, please, you must ask.